Hello, I'd like to explain the rigid body rotational motion experiment. First, the setup is a rotational apparatus that's made up of a big metal disc with two plastic drums on one side glued to them. And on the other side, there is this stick that can be fastened using clamps onto a metal stand. So this is the apparatus. And so this apparatus is very well lubricated so it can rotate with minimum friction. So we treat this as a frictionless rotation. So this entire object is called a rigid body. And from now on, we're going to talk about the three parts of the rotation. That is the metal plate, the plastic drums. One is slightly bigger, the other is slightly smaller. So these three objects glued together makes up the rotating rigid body. Speaking of rotational motion, I want to make sure we review these physics laws that helps us to understand. So first part is the quantities of angular speed and angular acceleration. And the next part is the physics law. These three equations of motion, 7.7, 8, and 9. These are the equations of motion for rotation under constant angular acceleration. So that's the type of motion, or in other words, that's the pattern we're going to use and to solve the lab problems. And number 3 is the relation between angular and linear quantities, particularly for velocity. The linear velocity in equation 7.10 equals to the radius multiplied by the angular velocity omega. That is not a W, that's a Greek letter omega. And in 7.11, the linear acceleration A equals to the radius r multiplied by the angular acceleration alpha. Again, that's a Greek letter alpha. So 7.1, 7.2, 7.3, these are the relevant part of the physics we're going to use in solving this lab problem. Okay. Interestingly, this is a very classic experiment to measure rotational motion. You have to know, 100 years ago, there were no cell phones, there were no sensors, there were no rotational sensors. So the way to measure rotational motion is actually very cleverly designed experiment to translate the rotational motion into linear motion because we're much better at measuring linear motion. So this is therefore the apparatus. There is a string that's fastened onto one of the plastic drums, and that becomes what we call the driving drum. Driving means when we pull the string, we ended up turn the entire apparatus. So whichever plastic drum we wind the string around, that is called the driving drum. And the entire apparatus will actually rotate at the same angular velocity because they're together. That is to say, this experiment is called a rotational motion. But through this well-designed experiment, the rotational motion can be measured by linear motion. So the actual measurement in this experiment is actually to measure how much this hanging piece of cylinder moves in the vertical direction. That's the delta y. And from the Newton's law, we can actually tell this rotational motion is under constant angular acceleration, and the linear motion is under constant linear acceleration. So that's the two patterns. The linear motion is a linear motion with along a straight line or so. Speaking of linear motion, then here I want to make sure you have these equations. So this linear motion is a one-dimensional motion with constant acceleration. That's the pattern. And the physics law are these three equations, 2.6, 2.9, and 2.10. When we solve the linear motion problems, we need to use these equations. So in summary, we are performing an experiment to study rotational motion using this well-designed rotational motion apparatus. In this apparatus, you need to know a few words. First is called the driving drum. That's the plastic drum where we wind the string on. And there's a metal plate and there's another plastic drum. This experiment can be run in two different ways: to wind the strings on the bigger plastic drum or wind the strings on the smaller plastic drum. This apparatus is actually pretty heavy. So it's extremely important that when we fasten this whole thing onto the metal stand is properly put so that it's stable. Although this is metal, but it can break if we somehow accidentally drop it to the ground. So it's very important that we keep it safe. Okay, so this is the apparatus. We need 7.1, 7.2, and 7.3, these theories, in order to translate this rotational motion to linear motion. In other words, instead of directly measure the rotational motion, that's what we're studying, we're going to using 7.3 to translate the velocity, acceleration, and also displacement into linear motion. And therefore, the measurement has been simplified to measure the linear motion of this hanging object at the end of the string. So we let go of the object and make sure we're going to measure it at the low point to see how much this object moves down along the y direction. And these are the equations for the linear motion we need to solve. The experiment is in the lab menu. Please follow the instructions. And these are all the patterns and physics laws we need in solving this real-world problem. Please ask any question if you have. Keep in mind, asking question is a strength. Every question is a good question. The only bad one is the one you have it left in your head. Okay, so now you got all the tools. It's time to start enjoying.